HRR deficiency and cancer, and about PARP inhibitors, and how we use this kind of assay in our lab. So as you probably may know, homologous recombination repair, HRR pathway, is present in all our cells to repair some single or double strand break in the DNA. And when we have this kind of alteration in the cell, we have this very accurate system that is able to repair the DNA by using the second gene that is still with no mistake, with no breaks. And so this system is very accurate and is able using proteins like BRCA1 or BRCA2 and other proteins involved in proteins like RAD51 and mechanisms. The cell is able to repair single or double strand breaks. And when this alteration is present, this HRR repair is able to repair everything and the cell can survive. On the second end, you have this PARP system, this other repair system that is able to also to fix the alteration on the DNA break. But this system is less accurate and is using PARP enzymes. And even if the system is used, the cell is still surviving. In cells with the HRR deficiency, the repair system is only using the PARP system, and the problem is that this system is less accurate. And this kind of, if the HRR is not working, then you have more genomic instability. The cell is still surviving, but the problem is that we have more genomic instability, and only PARP is working at this time. For cells with HRR deficiency, and also if you are using PARP inhibitors, then the cell will not be able to fix the alteration anymore. And in this case, you will get the cell won't be able to fix the alteration. And so it will lead to cell death. So that's what we call the lethality, the synthetic lethality in HRR deficient cells. And if the HRR is proficient, the cells can still survive because the homologous recombination repair is still working, even if you are blocking PARP with an inhibitor. So about PARP inhibitor development, so everything started in 1963 with the detection for the first time of the PARP enzyme in the nucleus. And then 1980, the discovery of benzamide as a competitive PARP inhibitor was starting the journey of PARP inhibitions in medicine. And in 1980, also the role of nuclear PARPs in DNA damage repair has been described. In 1994-1995, BRCA1 and BRCA2 were isolated for the first time, and it was, of course, as you know, something really important in science and in cancer particularly. Then in 2011, some preclinical data were available for BRCA1/2 deficient cells and sensitivity to PARP inhibitors. So. Finally, sorry for this, 2014, it was the first approval for the treatment of ovarian cancer after at least 3 chemos for patients with germline BRCA mutation. In 2016 and 17, the PARP inhibitors were used for treatment for advanced ovarian cancer, for germline and or somatic BRCA mutations, and also in maintenance for recurrent ovarian cancer in complete or partial response to platinum chemotherapy, regardless of BRCA, depending on the kind of PARP inhibitors used. Since 2018, you also have studies published with treatment for breast cancer for patients carrying a germline BRCA mutation and with a HER2 negative tumor. Also for maintenance for advanced cancer, ovarian cancer in complete or partial response to first-line platinum for both germline or somatic BRCA mutation, also for maintenance of ovarian cancer, regardless of BRCA status. In 2019, some studies have been also published for the treatment for advanced ovarian cancer with more than 3 chemotherapies and with HRR deficiency positive, which means that HRR is not working anymore in the cell. So it's a deficiency. And also in maintenance of metastatic pancreatic cancer of germline and all somatic BRCA mutations. So it's basically the POLO study. And finally, in 2020, the treatment for advanced ovarian cancer responded to platinum regardless of BRCA mutation, and also in male castration-resistant prostate cancer resistant to hormonal treatment, germline, or somatic HRR mutated. So now the fact is that most of these studies are focusing on BRCA, but we have much more beyond BRCA. And for example, in this paper published by the TCGA consortium in Nature in 2011, you can clearly see that we have much more issues than BRCA that makes HRR deficiency. And in this paper, they were able to show that the homologous recombination pathway were altered in up to 51% of cases of cancer. And finally, we had survival benefit for patients with BRCA or HRR deficiency. And some genes are involved like BRCA1, MC, BRCA2, RAD51C, PTEN, but FANC as well. Then in this paper published in the British Journal of Cancer in 2018, we can see that HRR gene mutations that are mutually exclusive to BRCA1 or 2. And in this slide, you can see each column is one patient, and 209 patients were involved in this study. And what is really interesting is the table on the right. So you can see that PFS, progression-free survival or overall survival, are quite different in these patients based on the BRCA status, but also on the HRR status. So if you check the hazard ratio here for BRCA mutant patients, the hazard ratio was 0.18 for PFS and 0.62 for overall survival. And for wild type patients, it was only 0.54 for PFS and 0.84 for overall survival. The results are quite similar with somatic mutations. And what is really interesting here is that we also have for BRCA wild type and HRR wild type, which is HR proficient, the hazard ratio is only 0.71 for the progression-free survival and 1.19 for overall survival. And if you check HRR mutant, which corresponds to HR deficiency, then you have 0.21 on the hazard ratio for PFS and 0.77 for overall survival. As you can see, a lot of genes are involved, so BRCA1, BRCA2, but also BRIP1, CDK12, or RAD54, RAD51, etc. And these genes are less frequently bearing a mutation than BRCA1 or BRCA2, but I think it's still worth to check these genes because it can explain whether HR is working or not in the cell. In this paper in Clinical Cancer Research in 2017, you can see that in ovarian cancer, overall all HR mutation rates, 23% were germline mutations and approximately 8% were somatic mutations. We also have patients that have both germline and somatic mutations in 1.1%. Among germline mutations, you can see that BRCA1 is more than 50% and BRCA2 represents more than 20%. And you have all these genes like BARB, CHEK2, and all the PALB2, RAD51 that are quite frequently mutated, but less than 5% most of the time. And considering somatic mutations, BRCA1 and BRCA2 are also the more frequently mutated. But you can see here that you have some genes like ATM or BRIP1 or CHEK2 that also are frequently mutated in these cases. If you want to check more than only SNPs and indels, this paper is really interesting. So it was published in Cancer Discovery in 2015, and the authors tried to separate HR deficiency, possibly HR deficiency, HR proficient, and the were also HR deficient. If you see the HR deficient patients, you can see that you have some BRCA1 germline or somatic mutations, of course BRCA2 germline or somatic mutations, but you also have promoter methylations in 10% of the cases of BRCA1, and then the other genes like CDK12, RAD51C, and these genes are all involved in the HRR. Interestingly, you can also see that loss of PTEN or amplification of MC are associated with possibly HR deficiency. And the conclusion is that approximately 50% of high-grade serous cancer, ovarian cancer, have an alteration in HR repair genes. In this recent preprint, you can see that in this pan-cancer analysis, so it's based on two public databases from the pan-cancer whole genome analysis and also the metastatic HMF database, and on ovarian cancer, breast cancer, pancreatic cancer, and prostate cancer, you can see that HR deficiency is quite frequent, which means that you are like 52 or 30%, depending on the 24 and 12% for breast cancer, 7.3 and 13% for pancreatic, and 5.6 and 13% for prostate cancer. If you consider all cancer, so all type of cancer, it's only 6.5, around 6% of HR deficiency. If you consider other cancer like head and neck or bone, soft tissue, liver, the HRD is not that frequent as well. And finally, of what kind of explanation we can have for this deficiency, for this HR deficiency, most of the time BRCA1, BRCA2 are the identified reasons of the deficiency, but also RAD51C and PALB2. So finally, if we want to sum up this first part, we have three different cases. If HR is proficient and you have a PARP inhibition, you don't have any effect. If your HR is deficient and you have a PARP proficient, then at this time you get a genomic instability. And finally, the last case, which is the synthetic lethality for cells, it's the HR deficiency, and if you use PARP inhibitors, then the cell goes to apoptosis. So what are the challenges in assessing HRR deficiency? It's important to say that an accurate detection of HRR deficiency is really relevant and important, and it will directly be indicative of sensitivity to targeted therapy with PARP inhibitors, as well as to DNA damaging reagents like platinum chemos. To avoid missing potential HRR deficient samples, future tests should encompass multiple loci, including somatic samples, expand gene sets, and explore multivariant types such as CNVs. Something that is questionable in the last published study is that some patients that are not identified like HR deficiency still benefit from PARP inhibitors. And it probably means that these patients may have HR deficiency, but we are not able to detect it in the right way. And it means that we need more better biomarkers to identify current HR proficiency status and further stratify cancer management. Nancy, France, in the east of France. And we are one of the French comprehensive cancer centers. It's a non-profit healthcare institution, and we are a member of the UniCancer group. We house all the human and technological means involved in treatment, education, and research in oncology. And talking about HRR, 70% of the samples we are analyzing are ovarian cancer, 20% of breast cancer, 5% of prostate cancer, and 5% are pancreatic cancers. So we decided to work with a custom-made SOPHIA HRS solution for SNVs and indels, and this panel has 20 genes, and the 20 genes are on the right. So you have, of course, all the genes involved in HRR, like ATM, BARD1, BRCA1, BRCA2, BRIP1, CDK12, CHEK1, CHEK2, FANCI-A, FANCI-L, FANCI-B2, MRE11A, and then PALD2, and all the RAD51 family, and also RAD54 and TP53, which is quite informative in some cases. And the idea was first to check only SNVs and indels, and finally we evolved to add the CNV detection. So basically, we are working on cancer, so CNV is maybe not the right term. I would prefer to say maybe somatic copy number alteration, since we are talking about tumor and not germline, but I will use the term CNV in this presentation. And this assay is a capture-based assay, and it's based on the SOPHIA platform. So, and we have like an all-in-one platform to do it, and all the files are uploaded on the SOPHIA Genetics data center, and we are only we can only access this data, and this data still stay private for our lab. We still own the data. So really briefly, to talk about the workflow for capture, the first step is samples. Then we use an enzymatic fragmentation. We do the N-repair tailing ligation cleanup to get the library, and then we do after cleaning, we just pull the library, then hybridize with target spawn to sequence. Then finally, we use a DNA beads capture and sequence everything in our Illumina-based system. These are indels, and it's really easy to get an interpretation. So I put one of our case of patients with a RAD51C mutation, and in this case, it was a mutation that leads to a terminal codon, which is literally pathogenic for the patients. And since RAD51C is not working in this case, we know that the patient has HRR deficiency. So you can see, you can identify, of course, nonsense mutations, missense, splice donor, splice acceptor, or synonymous mutations. But to look further and check CNV, this is the principle of the CNV analysis for these samples. So it's basically based on the analysis of the coverage levels. And the reference samples are automatically selected for each sample based on coverage patterns, similarity within the run. Coverage is then normalized by gene and by target region within the run. And the platform is able to detect breakpoints and assign the most likely copy number to each target region. So to make it really simple, finally, the software is checking the depth and the coverage for each part of the panel, and is able to see when you have some loss in the coverage or gain in the coverage. And you can see at the exon level that, for example, for this sample, on RAD51B, you have a loss in exon 8, 9, and 10. And also in RAD51B. So in this run, it's an example of a validation run we did a few months ago now. Sorry. And we used 24 previously characterized ovarian cancer FFPE samples. We also used commercial controls and previously characterized germline samples from patients that were treated in our institute. So at the end, you have this kind of figure, which have a lot of information. And on the left, you have the number of the sample, the identification of the sample, and then you have here all the panel and the coverage, which means that all the targets we are interested to. And if you zoom on this part, you can see, for example, for these samples that we have a gain for fancy L or fancy D2, for example, and also here are NBM. On this sample, you can see that we have a loss on RAD51B, for example. And for these samples here, we don't have any CNV identified. If we check more samples, we can see here that we have a loss of PALB2 in this sample, which was a germline sample from patients with already identified PALB2 loss. If we look per sample, it's quite easy to see as well, because we just have a table like this that summarizes everything. And we, for these patients, for example, for this sample, we have here again the 2.7 on NBN gene on the region exon 2 to exon 6. As you can see on this figure on the right, that you have the mean coverage here. And for this part of the gene, so from 2 to 6, you have a gain of copies for this part of the gene. If you look at these results for the sample 1908-22-4, we found fancy L and fancy D2 amplifications. As you can see here, this is the normal coverage for all the samples, and we have some extra coverage here and here. So exactly on exon 1 of fancy L and fancy D2. For this sample, it was also identified, so the PALB2 deletion here, which is like a loss of 1 copy of the gene, and a gain here of BRIP1. So finally, the take-home messages for this part would be that the CNVs were detectable on several samples that we assessed. The data were reproducible, so I did not show you here the reproduction of the assay, but all the samples gave exactly the same results. And we found gains or loss, and the good thing is that it's visible at the exon level, so we are able to exactly know where is the gain or the loss, which is really informative. And also, we are still confirming using CGHRA or FISH the result we had here on these samples. So what are the benefits of broader variant detections? Of course, SNVs or index are always informative, but more knowledge is required for variance interpretations. In silico tools are just tools and cannot replace real-life observation of functional tests for not previously described variants. So when you find a variant that is already identified in class and already identified in the database, so it's quite easy to predict what will be the effect on HR repair. But most of the time, since these genes are quite new for people that are sequencing tumors, it's quite difficult to make the prediction to know whether HR will be proficient or deficient. And even if you use in silico tools, it's not always easy to know whether the variant will be pathogenic or not. So we published a few weeks ago with my colleagues in Paris this paper in Journal of Molecular Diagnostics, and in this paper we evaluated different bioinformatic tools that are able to predict the pathogenicity of some variants. So for this, we use 4,000 somatic SNVs described in database and classified as oncogenic for almost 3,000 variants, or neutral for more than 1,000 variants. And here are the results of this study. You can see that the sensitivity is very different depending on the software you are using for the prediction, and as well as the specificity. And you can also find, for example, in the SOPHIA DDM software, this kind of presentation on your left. And this is a way to present the combination of different bioinformatics tools to know whether the variant you found is pathogenic or not, damaging or not. So what CNV assessment can bring? The CNV can be like a scar and can help for genomic instability estimation and determination. If you find also a loss on the key genes involved in HRR, it may have a serious impact on HR. Sometimes you can just classify the patients as HRR deficiency because of this loss. And of course, more knowledge is also necessary to predict whether CNV may lead to HR proficiency or deficiency. And here again, real-life observation of functional tests could be really helpful to know whether this alteration may have an impact or not. So I wanted to show this slide because it has been published a few days ago in Annals of Oncology, and it's really interesting to see where we stand in the HRD detection. And you have finally different strategies to know whether the patients have an HR proficiency or deficiency, and you have different tests for different informations. If you consider the mutations test, like the sequencing of a panel, you can identify some mutations on key genes and to predict pathogenicity. And finally, it's a way to know why it's not working. Then you have some functional tests, and at this time, with this kind of tests, you are able to know exactly at the present moment if HR is working or not, is proficient or deficient. And then you have the third kind of tests that give you an information about HRD or HRP, and it's based on difference and or genomic instability and different integrated genomic signatures. And these kind of tools will inform you if HRD was present or not, but it's more like a phenotypic test more than a genomic test, I would say, because you just identify that HRD was here, but you don't know if it's still here. And you also have some tests that are able to combine this kind of approach, so with the sequencing of key genes and also giving some genome instability scores or LOH scores. So in our lab, since we are sequencing the different genes and assessing the CNVs, we are able to make a kind of combined score to know whether HR is working or not. Finally, I wanted also to show this slide that is from the same paper, and just to remind that we still have some level of evidence for germline BRCA mutations in clinical validity, in first-line maintenance, and in relapse. Also for BRCA tumor mutations that have a good level of evidence. And then the non-BRCA mutations have a low level of evidence. And finally, the HR genomic scar assays also show a good level of evidence in clinics, in first-line maintenance and in relapsed disease. So genomic instability scores and LOH scores are also useful in clinics. So to conclude, I say that HR status is becoming very important to determine the potential benefit of PARP inhibitors. The SNVs or indels are always informative. The CNVs help to estimate genomic instability. CNV prime time readiness for prescription of PARP inhibitors. I guess it's only for clinical trials at the moment because it depends on the country you're working. But most of the time, the approval of the drugs now are based on the BRCA status and are not labeled for HR prescription based. Finally, the benefits of adding CNV and HRD or P testing, it allows us to save time and have a high accuracy. because everything is integrated with the rest of the analysis. We are also aware that more parameters shall be added in the future for a more exhaustive evaluation of HR functionality. And we also need expert recommendations because we need to know what score would be the best to define if HR is deficient or proficient. So thank you for your attention, and I'll be glad to answer the question if you have some questions. And once again, I'd like to thank GenomeWeb, Sophia, especially Michael and GB for the help in this presentation.
Yeah, thank you very much, Alexander. Very nice presentation. As a quick reminder, if you have a question, please type it into the Q&A panel. And we would also like to ask our participants to take a brief moment after the webinar has ended to take our exit survey and provide us with your feedback. So with that, let's see what we have here for questions. One general question about CNVs. What percentage of all mutations do CNVs account for in these types of cancers?
That's a good question. We don't have that much data published about this, but based on what we saw in the lab, we do have CNVs in approximately 20% of our samples. Mm-hmm. And it depends on, in ovarian cancer, we still have something like 20% of the samples that have CNV alterations.
Mm-hmm. And then a question somebody had about the data you showed for CNVs. Was that from FFPE samples or from germline samples?
So for the validation, we wanted to use both. We have FFPE samples with different quality. We use very good quality DNA and very low quality DNA extracted from FFPE samples. And we also use some DNA extracted from white cells from patients, so very, very good DNA. And we run both kind of samples in the same run just to make sure that the assay was able to give the results using both FFPE and germline samples.
Okay, we had a couple of general questions about HRD assessment. So what about using loss of heterozygosity, LST, and TAI status for the HRD assessment? Is that also being used? Mm-hmm.
This is a very good question, and these parameters are used in the commercial test. That commercial tests, and this is a nice way to see genomic instability and to give like a HRD score, because the more your genome is altered and the more LOH or the more telomeric fraction lost or large deletion you have, and the more your genome is not unstable. So it's a very nice way to check the phenotype, whether it's HRD or HRP. Mm-hmm. So yeah, it's something that you can add in your score, of course. But in the data I presented here, we just showed the SNV, invals, and CNVs, and we did not use this approach for the HRD mm-hmm. score.
Okay, understood. And coming back to the test that you used, did you use the Sophia DDM software to analyze the CNVs? And what is the minimum number of samples in one run to get at the coverage stability?
Okay, so we use for the analysis, we use the Sophia DDM software, so it's quite mm-hmm. easy because you just have to upload your FASTQ files through the software, and the analysis is automatically finished in less than 3 or 4 hours most of the time. For this assay, we are running 24 samples in one run in NextSeq 500 mm-hmm. instrument.
Okay, so, got it. Mm-hmm. Mm-hmm. And can you say something about the tumor purity of the samples that you assessed for CNVs?
Yes, so it's a very good question, because tumor purity is really a critical parameter to know to detect CNV. In these samples we use samples that were with 5% to 80% of tumor cells, but we used HE coloration to slides, HE slides to check the percentage of tumor cells. The problem is that it's really tricky to check CNV in this kind of sample because normal cells are not supposed to have copy number variations. And it means that if you have only 10% of tumor cells, if you have like a lot of gains, it will be easy to detect it, but the more challenging is to detect the loss, because the loss is finally lost in the signal of normal cells. So it's really challenging to be able to see loss in FFPE samples. And I mean, if tumor purity is low, it's really, really complicated.
Yeah. Is there a score to calculate the HRD in the SOPHIA pipeline?
No, not yet.
Okay. Maybe a future feature.
Yeah.
And I don't know if you addressed this earlier, but how do you actually differentiate germline from somatic mutations?
Yes, so most of the time we use the allele frequency to know whether it is germline or somatic, but even if you have 50% of 100%, you can't be 100% sure that this is germline. And the only way to really validate that the mutation is germline and not only somatic is to ask a blood sample from the patient. And it is also very important to be able to make the difference between germline and somatic, because the consequences for the patient's family are totally different when it's somatic and when it's germline.
And I guess there's a related question to that. Would you recommend testing both germline and somatic samples for patients, both in clinical trials and also in clinical practice for HRD?
Sorry, I don't. What is the question again? Sorry.
Whether you recommend testing for both germline and somatic mutations, both in clinical trials and also in clinical practice.
Okay. In our clinical practice, we are testing tumor first because it's easier for us and we can get the results more quickly than testing germline. But for patients with ovarian cancer in France, we recommend to have an oncogenetic consultation for all the patients. So most of the time we are running we analyze the tumor, and then if we find some alterations on DNA, then we ask the oncogenetic service to confirm on a second sample. So our strategy here is to do the tumor first and to run the germline then after.
I see, understood. Okay. And just coming back to the tumor purity question, what is the minimum variant allele frequency that you use in your panels for SNVs and indels?
Okay, so it really depends on several factors. The first thing is that since we are working on FFPE samples and different DNA quality, we don't have like a threshold of allele frequency. I would say that it's easy to say if there is a variant or not up to 1 or 2% of allele frequency, but it really depends on the sample, because if you have a very low DNA quality, sometimes you're not able to make the difference between a real mutation and background noise because of the amination or this kind of. So it really depends on the quality of the sample, and also it depends on of your DNA input, because we assume that we have like 300 copies for 1 nanogram of DNA. You can't really assume that you have like a 1% allele frequency mutations if you only have few copies of DNA to start. So for the sensitivity, the official sensitivity of our assay in our lab is around 2% for both indels or SNVs, but we have to make some updates based on the input DNA and also based on the DNA quality.
Okay, thank you. A couple of software-related questions. So you did mention before that you use the Sophia DDM software. Do you use any other software for the analysis? And the other question is, can't see that right now, but do you use any other software for the analysis?
So we are accredited lab, and we use the Sophia DDM software as the accredited process in our lab. But we also run some custom-made pipelines. So it's basically the standard pipelines based on software and ANOVA or these kind of things that are able to make like a custom pipeline, homemade. So we also were able to check the results we had with the Sophia DDM software using freeware available online.
Okay, thank you. ESMO guidelines on HR.
I think it's really interesting to get these recommendations, and I presented 2 slides with a part of these recommendations and some figures of this paper. I think it's a nice thing, and we should move shortly to HR determination, because it's really important for patients, and it's really important for the clinicians to know whether the patient will benefit from PARP inhibitors or not. So I think it's a good first step, and now we need more data to be able to so more data about it. And the second point is that we need like a clear expert recommendation to know how to build this HR score, because you have different way to do it. You have the commercial ways, and most of clinical trials have been validated with these commercial tests. And the problem with commercial tests is that sometimes it's not possible because of the law of the country. For example, you are not allowed in France to send a sample in a foreign country or use the results that have been produced in another country. So it's a problem sometimes of laws of your own country, sometimes a problem of money. And most of the lab want to be able to run their own score and manage their own samples from their own patients. So I think that it's really important to get these recommendations. It's a nice first step, and we need like new recommendations to know how to make the best score for HR and to be able to treat patients not only with the commercial test, but also with homemade tests.
Yeah. And maybe related to that, do you think labs in France will adopt testing of genomic scars, such as loss of heterozygosity, for clinical applications anytime soon?
Yeah. Already a few labs in France are running this kind of tests. So they are assessing LOH or large rearrangements or telomeric scars. So yes, some labs are moving in this direction, and it's a nice thing. And some labs in France still are only looking at BRCA1 and BRCA2. So some labs are moving in the right direction, and some labs are maybe more waiting for the wind to turn.
Maybe related to that, some labs only looking at BRCA1 and 2. What are the additional gains in HRD by adding somatic and non-BRCA genes and CNVs over and above just looking at BRCA mutations?
Yes, so it's a good question. In my talk, I presented some slides that show that you have like 50% of HRR deficiency and sometimes more in some cancer. And HRD is not explained only by BRCA1 and BRCA2, so it represents like maybe 80% only, or even less. And which means that if you only look at BRCA1 and BRCA2, you will see only 70% of the cases with HRR deficiency. And if you add the other genes that are, of course, less frequently bearing a mutation, then you add more chances to know whether HR will be deficient or proficient. So I think that in 2020, we can't just look just at BRCA1 and BRCA2 anymore, because we know perfectly that HR deficiency or proficiency can be also affected by other genes involved in the HR repair system.
Yeah. Speaking about those other genes, what are your thoughts on how TP53 may relate to HRD?
Yeah, it's a tricky question because TP53 is involved in so many biological processes. So I guess it's difficult to answer this question because it's not officially involved, but the problem is that everything is connected. And for example, some people say that the MSI will be also a good way to identify patients with HRD or this kind of thing. So I guess the TP53 is always important to check because you can detect some oncogenic issues, oncogenetics, but TP53 is also informative on the way that the cancer has evolved and in clonal evolution and all these things. So I'm not able to tell you whether TP53 has really a role in HR deficiency or not. And I don't know if history is involved, but I guess there are so many connections that it's probably worth to check. But I won't say that.
Yeah, and you mentioned clinical trials. Are you aware of, or can you mention any clinical trials that are using CNV testing and evaluate CNV testing for HRD?
I think the best way would be to check on clinicaltrials.gov.
Right.
All the clinical trials are open. Then it's always complicated to know in what kind of clinical trials are using only SNVs or INDELs or CNVs. But in France, we have the great clinical trial that has been open now almost 1 year ago. And they are checking a lot of different things, and I think it includes the CNVs.
Yeah. Do you have any experience in using circulating tumor DNA for monitoring PARP inhibitor resistance during treatment?
That's another good question. So we are using liquid biopsy for minimal residual disease, and we have very few experience on patients with PARP inhibitors and for MRD, but you have at least 2 or 3 very interesting papers published in less than 6 months ago that describe the use of liquid biopsy to detect the PARP inhibitors resistance, and especially with the detection of reversion mutations in BRCA. And it's known that almost 40 or 50% of patients have resistance to PARP inhibitors. So you can detect it using a very nice way to detect the resistance to PARP inhibitors. We only run a few samples, but it's for the moment it's not something that we use in routine practice at the moment.
How is HR deficiency?
Yeah, so I think it's also a tricky question because HR deficiency is defined like deficiency of homologous recombination repair pathway. And the problem is that this definition can be a genomic definition, which means that, for example, you have some mutations on some genes involved in this pathway, and so you have some damaged proteins that are not able to play their role, and so the HR is deficient. And in clinical trials, most of the time, they describe HRD like it's more like a phenotypic definition and using the genomic scar as the definition of HRD. So I would say that my definition of HRD is that the fact that in the present moment, it means that the cancer we are treating and the tumor is not able to fix the DNA using this pathway. And it's more important to know what is happening in the tumor at the present time you are healing the patient, more than knowing like what was in the tumor maybe 5 years ago during the diagnosis. So it's important to work on fresh biopsies or fresh samples, or when I mean fresh, I mean treatments, like a biopsy you did recently and not working on samples that are 10 years ago. And so it's important to know exactly what is happening on the tumor, because it's always evolving. And the deficiency has to be described based on the most recent sample you have. So.
Mm-hmm. Yeah. Mm-hmm. Anyway, fair enough. Coming back to the assay you use, what is the minimum sequence coverage that you considered for the validation? Is it like 1,000-fold or less?
We use a minimum of 500x.
500x. Mm-hmm.
Yeah, most of the time we used to get more than 1,000x.
Mm-hmm. Okay, good to know.
500x is the minimum, because otherwise, when you have, it's really complicated under 500x, especially on FFP samples, to make really sure that the variance you have is a real variance. To avoid confirmations, we like to get at least 1,000x.
Mm-hmm. Okay. And generally speaking, what would you say is the advantage of including CNV in this analysis and not run a separate assay for CNVs?
We are saving time and money, because
right.
Yeah, because instead of running the sample a second time for CNV, we have all in one. So we are saving time, money, and we are also saving something really important, that is the sample, the patient sample. For ovarian cancer, most of the time you have like a surgery or something, so you can have a lot of sample. But in some disease like prostate cancer, or sometimes you just have few tissue and very few DNA, because we are saving also we are giving more chance to the patient to get all the results with only the small sample we have.
Mm-hmm. Okay. And what are your next steps with using this panel?
The next steps, I have a lot of ideas of things we could add into this panel, because CNV is pretty nice. SNV is indels, and so the next step for me would be to add some LOH, some LOH, or large rearrangements, or large scale transition, or these kind of things, because the best way would be to have a very exhaustive view of the HRR proficiency or deficiency. And I'm pretty sure that if the more biomarkers we have and the more parameters we'll have, and the more we'll be able to identify the patients that will really benefit of this kind of treatment.
Okay. Mm-hmm. And maybe this could be the final question. Let's see. Do you have any advice for anyone who's thinking about detecting CNVs in somatic samples, how they should go about it, anything they should consider?
Advice? Well, yes, I think the best way to start is to have correctly characterized samples, and samples you already know, and you're able to run several times to know whether your assay can be reproducible and you have a good repeatability of the assay. And also it's good to know the mutations you're expecting, and also to know the variation you are expecting, because it's better to make this validation in a not blinded way. Like good samples already characterized, and then it can be very quick to start this kind of analysis, because if you know how to do NGS, finally you don't have that much difference between what we are doing. It's exactly the same thing, and everything is bioinformatics that is changing in this way. So yeah.
Okay, thank you. Actually, we do have a couple of questions that just rolled in. One is, if you find a mutation in your panel, does that actually mean the patient will respond to PARP inhibitor treatment?
Well, it depends on the mutation, of course. But,
Yes.
yeah, but sure, if we find a mutation that is definitely pathogenic and on the key gene of HRD, we will assume that HR will be deficient. Since we don't have that many database at the moment, because people are just starting. I mean, even if we have like TCGA database or ICGC database or a lot of genomic database, it's really complicated to find really good cured database. And it's something we started in France with a database. It's called SOVAD. And we started to get all the variants, like unknown variants and rare variants we found in different platforms in France. And every month we have an assessment meeting, and we are looking at all the variants and try to give a score, a pathogenicity score with this variant, and to be able to predict the best way as possible to the impact on HR.
Mm-hmm. Okay, thanks. And then finally, does the assay you used apply unique molecular identifiers?
Not for FFPE samples and not for tissues, but for cell-free DNA. Yeah.
It does. Okay. Mm-hmm. Yeah. Let me see. I think this is all the questions I have. Oh, actually, let me see. I think there are just a couple of questions that just came in. Here. What fraction of HRD positive samples do you expect to miss without checking for genomic rearrangements in other regions of the genome?
Yeah, it's hard to answer this question, but it's we miss some samples of some HRD positive samples, of course, and the best way would be to assess everything, of course. So with the solution we have at the moment, we know that we are missing some HRD positive samples, unfortunately. And I guess that we have to find a balance between doing in our lab for a good price and with instruments we know, and sending samples that is not possible for all patients.
Okay, great. Yeah, so this brings me to the end of the webinar because we have run out of time. So thank you very much, Alexandre, and also thank you to our sponsor, Sophia Genetics. And if we didn't get to your last-minute question on this, we will try to. Reminder, please look out for our survey back. And if you missed any part of this webinar, or you would like to listen to it again, we will send you a link to an archived version via email. So with that, thank you very much again for attending this genome webinar.